We've already seen cumulative probability functions for discrete random variables, but the definition in concept is the same for continuous ones. It's simply saying, what's the chance that any realization I may take of the random variable is less than or equal to some point I can choose. So in the discrete case, we had examples that were like rolling a die and saying, what's the chance that I see a number less than or equal to 4 on the die? Obviously, it's slightly different for a continuous case because I can't add up all of the probabilities less than or equal to the point I'm interested in. But we already have probability density as the, I suppose, continuous cousin of probability masses, and adding those up can't be done. I can't add these uncountable number of points, but the equivalent of summing would be integration. So I'm integrating the probability density all the way up to the point that I might be interested in. So this says that the cumulative probability function for x is obtained by integrating the density function of x between the smallest possible value, potentially tending off to minus infinity, and the point I'm now interested in, little x. Now some people here will see what's t. There's no t in the original question, but of course if I perform a definite integral, f of t dt, and then substitute through the two limits, there will be no t in the final answer. It's a dummy variable that will integrate out. I will tend to do that rather than integrating f of x with respect to x, and then substituting through a limit which is also x. You'll see the same result, but it's a bit sloppy, so I'll tend to do as most mathematicians would do, and just use a dummy variable that will integrate out. And then we've got our good friend, the fundamental theorem of calculus, which is effectively reminding us that differentiation and integration are inverse processes, that if I obtain the cumulative function by integrating the density function, then if I want to go the other way, if I've got the cumulative function and I want to go back to the probability density function, I can just differentiate it with respect to, well, in this case, x. So we'll actually start now with the uniform variable itself. So we've discussed this already in the subject, but only really, I suppose, as a tool of generating simulated randomness and not as a distribution really in its own right. So I'll start with a nice simple case of a uniform variable. I won't start with the uniform 0, 1. I'll start with the more general case of the uniform defined on the interval a to b. So a is less than b, so a is the lower limit, b is the upper limit, and all outcomes of x will be between a and b. And again, without any particular bias in that. They won't all be close to b or all close to a or all close to the middle. They'll be anywhere on that interval with equal chance of being, if I pick any two intervals of equal width, the outcome is equally likely to be in the two intervals, in each of the two intervals. So again, it looks like that. It's a rectangular slab of probability density, no chance of a result below a, no chance of a result above b, and the density is 1 over b minus a between them because, well, the area has to be 1, and so if it starts at a and ends at b, it's length b minus a. I hope we can all work out the area of a rectangle to be the base times the height, so b minus a has to be multiplied by 1 over b minus a to give area 1. So that is the density function of a uniform variable between A and B. Well, I can show that this is a valid density function by integrating it and showing that it integrates to 1. You can check my univariate calculus if you like, or you can look at that and say it's a rectangle, base times height is 1. The expectation, again, a bit more calculus, but the answer I hope is quite obvious, that when I've integrated x times the density function, which is how I calculate the expectation, integrate x, f of x with respect to x, over the full range, which technically is minus infinity to infinity, but in fact there's nothing below a and nothing above b, so there's no point in integrating the zeros. So if I integrate that between a and b, and sure enough, I will get b plus a over 2, which is the middle of the rectangle, basically the average of a and b. The average outcome is the middle of the rectangle. That's fairly obvious, I would hope. I would hope even if you hadn't done the integral and you were asked to say what the average value would be, you may be able to reason to that. If I want the cumulative probability function, there's actually 3 regions to work out, although 2 of them don't need a calculation. If I pick a point that's smaller than the smallest possible value, so less than a, the chance that my result is less than or equal to this point is 0. I cannot have an outcome smaller than the smallest possible value. If I pick a point that's bigger than b, so larger than the largest possible value, the chance that my result is less than this point is certain. In between a and b, well, I've got to work out how much of that rectangular slab of probability density I've passed so far. So if the point is between a and b, if I pick a point x in there, I need to integrate between a and x. So if I do that, I'm just integrating the constant 1 over b minus a with respect to t, so I'll get t over b minus a between the 2 limits of a and x. But if I plug those through, I'll get x minus a over b minus a. And the point about it is I've got a few inbuilt sense checks. The point x equals a is at the very bottom of that middle interval, but it's also the limit point of the 0 at the top, the limit point of the set describing x less than a. And sure enough, it joins up nicely. If I set x equals a in there, I'll get a minus a over b minus a. It matches up at 0. At the other end, x equals b is the limit point of the second and the third region here, and it should match up at 1, and sure enough it does. That I've got a 1 for x greater than b, and I've got a b minus a over b minus a for x being between a and b, so it matches up. So it looks like this. There's no sort of breaks. So it's a flat horizontal line below a flat horizontal line above b, and this continuous constant gradient, between a and b. We saw previously that we could generate realizations of a discrete variable from the cumulative probability function by effectively throwing a dart at the vertical axis between 0 and 1, uniformly selected over that region, and then drawing a horizontal line across and reading off where it met the cumulative function. Now, we said for the discrete case this was possibly an overcomplication of an idea that we'd already seen. But the reason it's useful is for the continuous case, because if I think of the continuous case, I can still apply the same rule and the same idea. Pick a point somewhere up the vertical axis, uniformly chosen. So I don't know what this point is, it's about 0.7, maybe a bit less. And I want to say, I want the point which is at about the 70th percentile of this distribution. So if I do that and read down, then what I will get to is I'll get to the point down here. But what is that blue curve? The blue curve is just the cumulative probability function. Now, usually if I plot a graph, I would think of the horizontal axis being the input and the vertical axis being the output. I've kind of got this one backwards. So what I want to do is I want to say, I don't know at this stage what the variable's value x is, but I pick a uniform point, and in this case I say I pick about 0.7. So I want the point which is at the 70th percentile of the cumulative function. So I want to read the graph backwards, if you know what I mean. Rather than putting a point in horizontally and reading off vertically, I pick the vertical value and read off the horizontal value. So the way we do this is we find the cumulative function and then invert it, and we find the value of the inverse cumulative at my uniform point.